Welcome back everyone. In this video, we're going to solve and analyze 3 string questions that you might get asked in an interview. Let's get into it. For question 1, since many interviews will let you use a programming language of your choice, I'm going to solve this problem with C. Now, I'll break down a solution and then discuss a common mistake new programmers make. Firstly, we know we need to go through the whole string, so let's get the length of the string and create a for loop. We also know that we need to count each letter and that each letter that appears in the string will have a count of at least 1. So let's create a variable to hold that. Now we want to start the for loop at the second letter, as in the for loop we're going to check if the current letter matches the letter before it. If it does, then we can increment the count. If it doesn't, then we can print the previous letter with the count and then reset the count back to 1 for the new letter. Now when the loop ends, we wouldn't have triggered this condition to print the final letter and count, so we need to do that as our last step. Analysing the complexity of the solution, both our letter count and string length variables are constant size, so our auxiliary space complexity is a constant, or O of 1. The space for the input grows linearly with the input itself, making it a linear relationship, or O of n. So combining that with our auxiliary space gives us a total space complexity of O of n. Regarding time complexity, in C, the string length function loops through the entire string, therefore it is O of n, and we loop through the string again in our for loop, which is also O of n. Everything else executes in constant time, thus the total time complexity is O of n. Now the common mistake people make is they calculate the length of the string in the for loop like this. Now unless the compiler can detect that the length of the string never changes and optimizes this loop, the program will call the string length function every iteration, changing our time complexity from O of n to O of n squared. So let's not do that. And now that our solution is done, we can watch it in action with this quick simulation. Question 2 involves determining if 2 strings are anagrams. A simple approach would be to sort the 2 strings letter by letter in alphabetical order, and then loop through them at the same time, checking that each letter matches. However, the time and space complexity of this approach is very much dependent on the sorting algorithm chosen, and if the language doesn't have a built-in implementation of our desired algorithm, we would have to create it ourselves. Another approach is to allocate a frequency array with a space for 26 integers, where the first element represents the count for the letter A and the last element represents the count for the letter Z. We can then loop through the first string and increment the respective count in the array each time we encounter the corresponding letter. We then loop through the second string and decrement the counts in the array. Once we have completed looping through both strings, if all the counts in the array are 0, we know that the 2 strings are anagrams. This is a great solution, but a drawback is, if we don't encounter all 26 letters in the alphabet, then we have wasted space in our array. An improved solution is to use a hash map rather than a frequency array, where we use the letter as the key and the count as the value. This ensures we are only allocating space for letters that are actually in the strings. Let's implement that, but this time let's do it in Python. We will start by checking if the 2 strings are equal length. If they are not, we know they can't be anagrams. If they are the same length, then we can proceed by declaring an empty dictionary, which will be our hash map. Then we will loop through the first string, using each letter as the keys for our dictionary, and every time we encounter that letter, we will increment the count by 1. The get function here returns the value for a given key, and returns 0 if the key doesn't exist. That way, when we encounter a letter for the first time, we can set the count to 1. We will then loop through the second string, and for each character, check if it is a key in the hash map. If it is not, then it wasn't in the first string, or if it is, and the count for that letter is already at 0, then we have an extra occurrence of that letter in the second string, and we can return false as the 2 strings can't be anagrams. If the letter passes these checks, then we instead decrement the count for that letter. Since we checked the strings are the same length, as long as none of these checks fail in the second for loop, then the 2 strings must be anagrams and we can return true. Let's analyse the complexity of this solution. Regarding auxiliary space, the only variable we declare is our hash map. Typically, hash maps have a space complexity of O of n, as the keys can grow linearly. However, in our case, we can have as little as 0 keys and at most 26 keys, 1 for each letter of the alphabet, remembering that we are only provided strings comprised of lowercase letters. Therefore, the space of our hash map does not grow linearly with respect to input, and instead has a lower bound of 0 and an upper bound of 26. Therefore, we can essentially treat it as a constant, or O of 1. Thus, our auxiliary space is O of 1. Now the space complexity of our algorithm is dependent on our auxiliary space and the input size. Since the inputs can be of different sizes, their space complexity is O of n and O of m, where n is the length of string 1 and m is the length of string 2, making our overall space complexity O of n plus m. If string 1 and string 2 are the same length, then our space complexity is O of n. Regarding time complexity, the keys in our hash map only have one value that is incremented or decremented in the event of any collisions. Thus, search and insertion both take constant time, or O of 1. Now, unlike what we saw in C earlier, the length function in Python executes in constant time, thus getting the length of the two strings is also constant. If the two strings are not the same length, our function will end and never reach the loops. Thus, in the best case, our time complexity is O of 1. If the two strings are equal length, then we reach the first loop, which iterates through the entire string, giving us O of n, and then we iterate through the second string, which in the worst case will iterate through the whole string, also giving us O of n, and in the best case it will terminate at the first letter, giving us O of 1. Therefore, best case time complexity is O of 1 and worst case time complexity is O of n. Let's now see the solution in action. Thinking about how we could solve question 3, we obviously need to loop through the string and make sure that all opening characters have a corresponding closing character, but we also need to make sure they're in the right order, which we can do by keeping track of all the opening characters, and whenever we encounter a closing character, we can check if it is the correct match for the most recent opening character. This sounds like a great use for a hash map and a stack, so let's implement that, and this time we will choose C++. We will start by defining our hash map, with the opening characters as the keys and the closing characters as the values, and then we will create a stack. We will loop through each character in the string, and if the character is a key in the hash map, then it must be an opening character, and we will push that onto the stack. Otherwise, it must be a closing character, and so we check if the stack is empty, meaning there is a closing character without a corresponding opening character, or we check if the closing character does not match the corresponding opening character in our hash map, meaning it is in incorrect order. Thus, if either of these conditions are true, we can return false. If, however, it passes these conditions, then the closing character must match the most recent opening character, and we can pop that off the stack and continue through the loop. After looping through the entire string, we finally check that the stack is empty, meaning that all opening characters had a corresponding closing character in the correct order, and we can return the result of this check, which will be either true or false. Let's analyze the complexity. We use two auxiliary variables, one for our hash map and one for our stack. Our hash map will always be the same size, but our stack is dependent on the input. In the best case, our string is empty or consists of only closing characters, meaning our stack will always be empty or O of 1. In the worst case, our string consists of only opening characters, which will all be pushed to the stack, and thus being O of n. Therefore, our best case auxiliary space complexity is O of 1, and our worst case is O of n. Our input also has a space complexity of O of n, giving us a total space complexity of O of n. Regarding time complexity, searching the hash map, pushing to the stack, checking the top of the stack, popping from the stack, and checking that the stack is empty all takes constant time, giving us O of 1. However, the time complexity for the for loop follows the same logic as the space complexity for the stack. In the best case, we have an empty string or only closing brackets, meaning the loop runs once, giving us O of 1. Worst case, we have only opening brackets or the string is valid, so the for loop iterates through all the characters, giving us O of n. Thus our time complexity is O of 1 in the best case and O of n in the worst case, and we can see this solution in action now. And that concludes this video. If you enjoyed this breakdown and want to see more videos like this, then let me know in the comments below. Otherwise, check out one of my other videos for more computer science goodness.